Hello everyone, welcome back to another lecture of COP-3402. Today we're going to be continuing from where we left off last time, talking about how compilers actually translate the code that you write, for example C code, into the machine code that your processor can actually execute. So before we get into the details of that and how compilers actually do this, I want to reiterate a point that we had talked about last time, that symbols do not inherently have meaning. We give symbols meaning. So to illustrate this concept, I want to show some programs here and references. So the first program I want to show is the octal dump program. So let's look at the contents of this file I prepared here, hello.c. It just contains the C code for hello world. And now let's use the octal dump program to view the octal contents of this file. You don't need to know this for an exam or anything. I'm just trying to make a point here. What we will see here is a bunch of octal code on the left and the ASCII representation of this octal code on the right. So does this octal code contain the machine code for actually executing this C code? No, right? This is the octal code behind the representation of this C code, the ASCII representation. So again, we can look at the ASCII table, and you can see there's a whole listing here of the different ASCII characters and their hexadecimal and octal codes. So this code here is not the actual code you would run in your processor to execute this C code. It is just the octal code behind the ASCII representation of this C code. So another example would be if we were to run gcc with the -S flag to translate our hello.c file into an assembly file. We can call it hello.s. And then if we view this file, I'll view it in less, hello.s, we can actually see the assembly contents of this file. So the original C code translated to assembly. But again, is this the code that our processor will actually run? No, right? This is still a human-readable representation of our code. Granted, the machine code is going to be a pretty close mapping to the assembly code you see here, but it's not the same thing. I know I've said this before in the previous lecture, but I want to make it very clear that there is a distinction between the symbols and the meaning we give them. That's very important for the latter half of this course because we're going to be giving a bunch of symbols meaning by writing a compiler. So how do we actually do that, though? How do we actually give these symbols that we see meaning? Well, the primary way we do this in compiler design is through creating syntax trees, parsing our inputs into syntax trees. And to illustrate this concept, I want to take a step back from coding and talk about human languages. So you might have learned this in grade school, but there's actually a way to form these sorts of syntax trees out of human phrases as well. Human sentences as well, I should say. So let's look at this example here. We have this short sentence, the boy went to the store. The first thing you want to do, if we want to try and derive some meaning out of this sentence, and you probably do this in your head without even realizing it, is to identify the parts of speech that each of these words in this sentence are. So I'm going to draw these in blue to make it clear. For example, the boy would be a noun. The store would also be a noun. Went would be a verb. The word the would be an article. I'm actually going to abbreviate that because article is a long word, so I'll just use art there. Put it there as well. And to is what's called a preposition. You might have learned to do this sort of sentence diagramming in school. I don't know if they teach it much anymore. I don't think I learned it in elementary school or grade school at all. I think some people might have, but I don't think I did. But it's useful here for illustrating this idea of syntax trees. So let me actually draw some arrows to connect these parts of speech to the words they are associated with. So the noun, boy is a noun, went is a verb, to is a preposition, art is the, or the is an article, and store is a noun. Now we can go one step further here, now that we've identified the parts of speech that these words belong to, or that they are. We can actually group these words together, right? So for instance, maybe this part at the end here, this is a noun phrase, let's say. I'll make this centered so it's nice and pretty. I'll center these as well. So having a, combining an article with a noun forms a noun phrase. And if we're combining an article with a noun to form a noun phrase, we can do the same thing over on the left-hand side here. The boy, the store are both noun phrases. And then maybe we treat the verb went as just a verb phrase by itself. You can see we're already starting to form this sort of tree structure. And now what we can do to go one step further here is say, okay, this noun phrase is the subject of this sentence. So you might at least remember that each sentence, every sentence in English, is supposed to have a subject, verb, and an object. So what does that make this? Well, that makes all this the object. So let me put that over here. Make this a little bit smaller too, a little bit closer, more shallower. And technically this would be an indirect object actually. And what this would have, what we will put here to form this indirect object is the prepositional phrase, or preposition I should say, and the noun phrase, the preposition and the noun phrase. And now that we have a subject, a verb, and an object, we can form a sentence. This is sort of like the ultimate, the root node of our tree, you can think of this as. So I don't know if you learned this earlier in grade school or whatnot. Not really essential, I guess, for this course to know how to do this for human language. But this idea of forming a syntax tree out of some given input, some given text, is going to be vital for the latter half of this course. So if you don't need to know how to do this for English, but you will have to at least understand how to do it for programming languages in general. So let's go back to the slides before we proceed here in the drawings. So like we saw, there is one sentence type, but there's different parts of the sentence. So we had under our sentence a subject, a verb phrase, and an indirect object. And there's different kinds of subjects and objects, right? Like we don't necessarily need a noun phrase here. This could be a proper noun. There's different ways you could change this. There could be adjectives, modifiers, all sorts of modifications you can make to the sentence, but ultimately it's still a sentence that we can parse. And just to illustrate this or reiterate this point, this syntactic structure captures the relationship between these words. So we know that the boy is the subject. He is doing something to the store. He's going to the store. And as humans reading the sentence, as English speakers at least, we can intuitively know that the boy is the one acting on the store. It doesn't really make sense. They're not going to say the store goes to the boy. You can think in other languages, like I think Latin or maybe Japanese, it's sort of reversed, where the object might be the one doing something to the subject. But in English at least, we say the subject first, then the verb, and then the object. And this can become more complex very easily. So, for example, we could say the boy leaving behind his friend went to the store. If we were to try and diagram this, maybe this would confuse a computer or some program thinking that leaving behind his friend is maybe the different object or a different subject. But we know that the boy went to the store is still ultimately the point of this sentence. Leaving behind his friend is just some extra details that we are given. Even without the proper grammar here, you probably want to put commas to make the meaning of the sentence very clear. We can still interpret this sentence and give it meaning. So again, ambiguity here. This is another example of how we can interpret language very impressively. What does the store mean? So there's different definitions of the word store, right? We have the noun, the store is closed, like we saw the boy went to the store, probably the same kind of store. Or we have the verb, squirrels store acorns for the winter. And I want to go to this next example here. This kind of relates to a famous quote from Noam Chomsky, famous grammatical person who's interested in grammar. Chomsky wrote in this book, in 1957, "Colorless green ideas sleep furiously, and furiously sleep ideas green colorless." His point of, really the first sentence especially here, is that you can make a sentence that is syntactically correct. There's no no syntax error in this sentence. You can read it as an English speaker. But its meaning, its semantics, is ambiguous. It's not, or at least nonsensical, pretty much. This doesn't really have meaning, but we can still interpret it. And so, of course, all this is to say the meaning depends on the structure we give our sentences. We give our input, whether it be an English sentence or maybe some code. So as another example, let's take a look at arithmetic. And this is not just limited to the English language. Let's look at arithmetic now. So we have this expression here, 9 plus 3 minus 2. How would we derive a parse tree for 9 plus 3 minus 2? Well, one way we could do it, the first thing we probably want to do is similar to how we derived a parse tree for the English sentence above, the syntax tree. We would start with identifying the parts of speech that these things belong to. So in this case, the parts of math they belong to. Let me just get this here. There we go. Or maybe a little bit bigger. All right, that's pretty good. So 9, 3, and 2 would be numbers. Plus and minus would be operators. And let's draw some lines now to connect these. So minus is an operator, and 2 is a number. Now that we've identified the parts of the expression, we can start grouping these together to give some meaning to them. So for instance, if we're doing this, if we're actually evaluating this in our head, what we might want to say is, all right, let's group 9 and 3 together immediately because we know that we're going to be adding or performing these operations in sequence. So let's just add 9 and 3 together first. We can call this an expression here, this grouping. I'll just say expr. And this is if we're interpreting this language in our head. We're interpreting this mathematical expression in our head. So 9 plus 3, what does that equal? Well, 12. So I'll just say 12 here. Actually, what I'll do is make sure it's the same size by just dragging this over. Make that 12, make it black. There we go. And now what about the second half of this expression? Well, we can think of this as being a recursive interpretation. So for instance, or I guess to illustrate this, we would basically take the whole expression as the whole sentence, I should say, this whole expression here as the top-level expression, where the left operand is in turn an expression, and the right operand is num, and the operator is minus. So we could draw that out like so. I'll make this blue again. Right here. And now if we evaluate this whole expression, we would get 12 minus 2, 10. And so now I want to take a second here to sort of emphasize something. Let me actually go to my pointer. Let me check the slide, see if there's anything else here that I should be saying at this point. Okay, not yet. So what are we actually doing here? What did we just do? We went down to the bottom, we identified the leaf nodes here in this tree, and then we recursively bubbled up and created this expression and evaluated it. So we started at the leaves, worked our way up to this expression, continued from these leaves, and then worked our way up to the top level expression of this expression here, this mathematical expression. So what this is called, you might have seen this before in CS1, I hope you did. This would be post-order tree traversal. That's what this is an example of. You've probably already seen this algorithm before. It's just a post-order tree traversal. And you'll see this actually come up very frequently in computer science, in parsing at least. That all we're really doing is just starting from the bottom and working our way up to some top-level parse, some goal that we're trying to evaluate, to recognize. So this is an example of how you could interpret this expression using syntax trees. Now, the question you might have is, all right, so what about compilation? How does this apply to compilation? Because we're not building an interpreter, we're building a compiler. So how does this apply to compilation? Well, the way it could apply to compilation is if instead of generating or evaluating the expressions as you proceed through this parse tree, the syntax tree, you instead evaluate or generate the assembly code for each part of the expression. So we would say, for instance, to evaluate this addition here, move 9 into RAX. This is like what we saw in the previous lecture, the assembly code we saw in the previous lecture. Move $3 %RBX, and then add $9, or not $9, add %RBX into %RAX and store the result in RAX. And then how would we evaluate this top-level expression here? Well, we'd have to plug in what we have on the left here. And I'm going to leave this as a question mark for now because we don't exactly know. I'm not going to go into it yet, but there's more steps involved when you're trying to evaluate sub-expressions. But the big idea is that we're just recursively emitting code for each of these sub-expressions as we parse them. So we'll see later in this course how you're going to fill in this question mark. But the big idea is that when you're evaluating these expressions, if you want to compile it, you would just emit the appropriate code for each sub-expression, each sub-part of this tree while working your way up to the top level of the tree, the root of the tree. So again, post-ordered traversal, that's what we had just done. The leaf nodes in this tree are going to be the numerals and the operators themselves, and the inner nodes are going to be the results of either interpreting or compiling these expressions, these groupings of symbols together, of tokens. Now, sometimes you can have ambiguity in your grammars when you're defining them. So to give another example here of this 1 + 2 × 3, I think I might have this. No, I don't have this drawn already. So I'll draw this quickly one way, and then we'll see another way in which we can represent this. I'm actually going to copy most of what I have here because I think a lot of it still applies. Just copy that. Take that, take that, take that, take that. Oops, lost it all. All right, that's pretty good. Let me drag that over here. Add another number right here. Okay, so this is one example of a parse for this input, 1 + 2 × 3. And how would we evaluate this? Well, normally, when we're evaluating operations, if you've learned mathematical operations in school, you would evaluate it as 2 × 3 first. But with this parse tree, this syntax tree, we're grouping 1 + 2 together more closely. So one way to parse this tree, actually, let me illustrate both the ideas here first before I go into the other idea. Another way we could parse this input would be to shift this expr over here and parse the grouping on the right first before we go for the grouping on the left. And if we do this, we can actually subtly change the meaning of this input, how our compiler would recognize it, or our interpreter. So we saw above, we evaluated, let's see, we didn't see I lost the interpreter example here, but we evaluated 9 + 3 first to generate 12, and then subtracted 2 to get 10. On this right-hand example here, what we would do is evaluate 2 × 6 first to get 2 × 3 first to get 6, and then add 1 to that to obtain 7. Meanwhile, in this parse tree, what we would do, if we were to do 1 + 2 first, we would have 3 evaluate here. 1 + 2 is 3. And then multiply that by 3 over here. Let me actually drag this 7 over to get 9. So you can see, like, the grammar is important. There can be no ambiguity in the grammar or the semantics of our language, otherwise we run into all sorts of problems. And we can actually encode this grouping, this appropriate order of operations, what we want on the right here. So I'll put a box around it because that's what we want. We can sort of encode this in our programming languages that we design. And we'll see how you can do that later in this course. But the big idea is that, again, this may not be wrong. Maybe we want to do this. It's just however we define our grammar, how we define our compiler to give meaning to these symbols. We're just trained as English speakers, as children, as humans, to evaluate mathematical expressions in this particular order. And so how do we actually do this sort of parsing, though? So we've looked at all these examples, all these illustrations. How do we actually perform this? What's the way we can specify the grammars in our syntactic structure, the groupings here of our input? Well, we don't directly ever say in our code or in speech, like if we go back up to the before we went to the story example, I don't say that's an article, boy, that's a noun, went, verb. Like I don't label every part of the speech as I speak. We are able to intuit this. There's sort of the unspoken parts of our speech here. I'll go back up to this sentence actually. So the way we can do this is, again, through parsing. We've seen all this, so I'm going to skip ahead a little bit here. We have to have a language for describing our grammar, our syntax. And we typically use like these 4 words to really describe it. This is sort of specific terminology, but I'm going to break it down and try to make it very clear. So first we have terminals. Terminals are going to be things like article and boy. So we'll say here, I'll actually label this to try to make it very clear what's the terminal. Let me actually make this a little bit bigger. So these are the terminals at the bottom. They are parts of speech, parts of a language, which can go no further. They are like the atoms of the language. They're what everything else is composed of. Then we have our non-terminals. These slides explain these, so I'm going to go through these one at a time. So the terminals, again, the tokens, the elementary components of our language. The non-terminals are syntactic structures. So for example, a noun phrase, a verb phrase, a noun phrase again. These are all groupings of syntactic structures in our language. They're not things that we explicitly ever say. And these are also non-terminals. So non-terminals really are just any of these interior nodes of this tree. You could even say that the sentence itself is a non-terminal. Often something like this, the root of a parse tree would be called the starting symbol. You'll often hear that. So for example, in a programming language, an expression, like we saw down here, this would be a non-terminal. Expr is a non-terminal, expr is a non-terminal, num, op, and num, these are all terminals. Or a function definition, that would be a non-terminal, because when you define a function, you have to give, there's many parts that go into defining a function. You have to give the return type, the name, the argument types, the body. That all makes a function a non-terminal, a function definition at least. Now we also have what are called mappings. So mappings are like the rules to generate a part of a language, a syntactic grouping. So it maps the non-terminals to their contents, defines the legal groupings, and we can typically depict this using an arrow. So we might say something like for expressions, and we're going to see another example of this later just to illustrate this maybe cleanly. We can say an expression, expr, is an expr plus an expr. So this would only support addition here, but you can get the idea. Let me actually make this clear. An expr plus an expr. And what is an expr? Because we're only defining this like recursively. We'll see that shortly in another slide. But the idea is that you have these production rules telling you how you can generate these groupings of language based off of existing non-terminals and terminals. And then we have, of course, the starting symbol, which I think that was in this slide up here. Yeah. So for the starting symbol, that would be, for instance, in the English sentence here, would be a sentence. So I'll just replace this with starting symbol to make that very clear. Starting symbol. So again, constructs can be nested. So like we saw in this example I drew down here, we can have expr recurse into the same definition of expr for doing addition. And how can we actually achieve a termination of this addition? Well, we have to use the terminals. So let's actually look at an example grammar here. We have an expression is an expression plus an expression, or, so we have multiple signatures for the same, multiple productions of the same symbol, that just means these are alternatives. So an expression can also expand or be derived from an expression minus an expression. And by minus, I just mean the literal character minus, the literal character plus, the literal character for multiplication, and the literal division symbol. And then an expression could also be an n, and an n is a production that comes from one of these terminals. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. These are all the different terminals of our language, and n comes from each of these. So this actually is a grammar suitable for parsing our input right here. So for example, we would say expr, I'll delete the quotation marks here, expr plus expr, expr minus expr, expr could also go to an n, and then this n could either expand to a 9 or 3, oops, 3, there we go, or a 2. And this is sufficient to actually parse this grammar. Now, one thing you might notice is that we say expr goes from n, so technically you probably want to put another intermediate step here where number becomes an expr and then that expr becomes an x, parts of this larger expr here. But I think you get the idea. So again, the way we derive this tree is to start with the start symbol and then just find a sequence of rules that we can apply, a sequence of these productions we can apply to generate this syntax tree, this parse tree. And what's important is that this has to completely parse the tree. There can be no token, no non-terminal left unaccounted for in the final production that we derive, or maybe the first production, depending on how you look at it, the starting symbol. And so the way we perform an interpreter, or we define an interpreter, would be to, like we saw earlier, just evaluate these steps one at a time. So 12 would be here, and then 10 would be here. We just evaluate the steps associated with each of these syntactic groupings as we walk the tree. I want to do that now. And this is some more technical stuff. Let's just assume this is a bit more complex, but I'll go into this example since we're in the video and I have the time for it. So let's assume we have some interpreter with some rules implemented, add, sub, some functions I should say, add, sub, mult, and div to perform standard arithmetic operations, and then a function ASCII to int to convert an ASCII character into its integer representation. We can actually define a grammar like this formally in C code, not really C code, but using the tool lex, using a syntax similar to this. So if I actually go back into my slides here, go back to the compiler basics, not compiler basics, but the proc assignment. So if I actually open this up, let's go to the proc assignment here. I'm going to show you something that I think is very relevant for this lecture. Let's copy some code. Let's get the code from the proc assignment. Go back to my slides here. I'll just make a directory called proc, cd into it. Copy and paste that command to get the proc code. And let's take a look at this lex.l file. You can see the syntax is not very easy to read, but the symbols here are not as obvious. These productions are not as obvious. But basically, we're doing what is in this code here. It's similar to the syntax for lex. We're defining some sort of computation for each of these grammar rules, each of these productions. So when we see an expression that is derived from an expression plus an expression, we set the value equal to the addition of the two sub-expressions, for instance. And now for defining a compiler, it's very similar. We're going down the tree, walking up, and we're generating code instead of computing a result. So again, you can see here, maybe in this case, to generate a infix to postfix compiler, or to define a grammar for an infix to postfix compiler, like the computations for actually performing that translation, we could use some sort of syntax similar to this. And this is basically what you're doing in your infix to postfix project into post. So the idea here is that when we see an expression like 1 plus 2, what we would do, if I can copy this here, 1 plus 2, maybe minus 3, No, we'll just say 1 plus 2, just keep it simple for now. Close this. If we have the expression 1 plus 2, we would concatenate 1 and then 2 and then generate it to plus. So we would say 1, 2, plus. And then depending on how we define our parse tree, we could actually generate more complex or bigger operations in different ways. So for this example here, 9 plus 3 would be 9. If we're handling this subexpression first, I'll actually label this here so you can see it very clearly. Oops, I'll make that blue again. 9, 3 plus would be on our left-hand side here. And then our right-hand side, it's a subtraction, so what's the rule for subtraction? Well, it's to take the left-hand side and then put the right-hand side afterwards and followed by a minus sign. So we would have 9, 3 plus 2 minus. But again, we could group this differently. So if I go down to the examples down here, let's say we evaluated this instead. Let me put these over here so we can illustrate a different concept. An asterisk here, we would represent using this operation here, this multiplication, we would represent as 2, 3 multiply, 2, 3 times. And then for the root, we would say 2, 3 times 7, or not 7, 1 plus, I believe. Actually, no, it'll be 1 plus 2, 3 times, because the 1 plus is on the left. Now what about in this other expression here? So if we grouped it differently, we would have 1, 2 plus, because we're deriving this tree. So 1 is the left-hand side, 2 is the right-hand side. We put the plus sign afterwards. And then we could evaluate this top part as 1, 2 plus 9, plus, not 9, 3 asterisk. So you can see how different ways that we parse our input generate different outputs. So again, the 1 comes from here, the 2 comes from here, the plus comes from here. And then in this case, we would take the sub-expression as the whole left-hand side, then take our 3 from here, and our operator from here. Whereas in this case, we're getting the 2 from here, 3 from here, asterisk from here, then treating this whole sub-expression as the right-hand side, and we get our operator from the middle here, plus, and then 1 from the left-hand side, plus. All right, and that wraps up this lecture. I hope that was a general introduction to parsing and derivation. You're going to be not having to write your own parser for this course. We're going to be giving you the code for a parser as well. Parsing can get kind of tricky. It's, I think, really fun to write parsers, but they can get kind of tricky to implement. So we're going to give you the code for a lexer and a parser. So for the project, you had to implement a parser, not for parse trees, but just a command structure you're parsing to, and we gave you a lexer. But for this upcoming assignment, for the compiler project, you're going to be given a lexer, and you're also going to be given a parser that will generate this tree structure for you. And then your goal is going to be to walk this tree to generate the appropriate assembly code for the instructions that you are walking over. So I hope that sounds exciting. I will see you all in the next lecture.